A hospital worker sets a freshly washed instrument tray beneath a bright lamp. Water slips from its corners, leaving a surface that looks still, clean, and almost empty. But the metal is not doing nothing. At its surface, it is reacting with the world around it. That reaction creates a barrier so thin that no eye can see it. The tray is made mostly from iron, the element we associate with rust. Yet chromium in the alloy helps build an invisible protective film. When mild damage breaks that film, suitable surroundings can let it form again. That is the limited truth behind a remarkable phrase. Stainless steel can repair its protective skin. It cannot refill a scratch, close a crack, or replace metal already lost. Its deeper achievement joins material behavior to human work. Someone chose the grade, shaped the tray, finished the surface, washed it, inspected it, and kept harsh chemistry from defeating it. That makes the quiet surface personal. Variations of it touch your food, water, medicine, kitchen, and public spaces. Their shine is dependable only while the conditions behind it remain dependable. Iron offered early societies a powerful bargain. It was abundant, strong, workable, and capable of becoming many steels. The cost appeared whenever water and oxygen reached an exposed surface. Rust is not just a stain placed on top of iron. It is the visible result of metal being converted into corrosion products. Those products often crack and flake, exposing more material beneath. People fought that process with oil, paint, plating, polishing, drainage, thicker sections, and replacement. Each solution could work, but each added maintenance or placed another material between steel and its surroundings. Chromium suggested a different possibility. Instead of hiding iron beneath a thick coating, metallurgists could change how the alloy itself behaved at the surface. Reaching that point took more than adding a special ingredient. Chromium, carbon, temperature, and manufacturing history interact. Early furnaces could not control them with modern precision. A composition that resisted one liquid might be brittle, difficult to shape, or unreliable after heat treatment. Researchers across Europe and the United States explored chromium-bearing steels. Some noticed unusual resistance to acids or atmospheric rusting. Their work formed a scattered path, rather than one clean march toward a known destination. In Sheffield, Harry Brearley investigated steels intended to resist erosion inside gun barrels. In 1913, one chromium steel became recognized for its resistance to rust. Cutlery soon offered a practical civilian use. The usual story turns this moment into a lone inventor finding an immortal metal. Reality was more crowded. Earlier experiments, parallel discoveries, furnace skill, rolling, finishing, and commercial persistence all mattered. Brearley's steel also was not the final answer. W. H. Hatfield later developed a chromium-nickel type known as 18-8. That name points to roughly 18% chromium and 8% nickel. Nickel helped produce an austenitic structure that was tough, formable, and useful across many temperatures. Other families followed different paths, trading nickel, hardness, strength, magnetism, weldability, and corrosion resistance. The breakthrough was therefore not a single recipe. It was a growing family of steels whose surfaces could remain stable enough for tasks that demanded repeated contact, cleaning, heat, weather, or chemical exposure. Cut through a stainless sheet in imagination. Most of what you enter is bulk alloy, iron-rich crystals containing chromium and other elements selected for a particular grade. Now, move back to the outermost surface. There, chromium is enriched within an oxide-rich region only a few nanometers thick. This is the passive film, a reacted layer that slows further corrosion. Passive does not mean chemically asleep. It means the surface reaction has become slow enough to protect useful metal beneath it. The film controls movement between the alloy and its environment. A light abrasion can remove part of that protection. Fresh alloy meets oxygen-bearing air or water. Chromium near the surface reacts, and a protective state can return. Repassivation is the rebuilding of surface protection after disruption. The scratch itself remains. Stainless steel does not grow back like skin, and a deep pit does not fill itself. The repair also needs favorable surroundings. On an open, clean surface, oxygen can support the passive state. Inside a tight, wet gap, the local environment may change faster than it can recover. Imagine salt water trapped beneath a washer. Oxygen inside the gap is consumed and replenished slowly. The liquid becomes more acidic and chloride-rich, weakening protection inside while the open surface still looks bright. This is crevice corrosion. Pitting follows a related local feedback. Chloride breaks down a vulnerable point, and the tiny cavity develops chemistry that drives attack deeper into the metal. That is why stainless can fail without turning uniformly red. A polished sheet may look sound around one dangerous pit. The visible shine can hide a highly local problem. Alloy choice changes the odds. Molybdenum can improve resistance to chloride pitting in suitable grades. Nickel supports useful phase structure and fabrication. Nitrogen can add strength and localized corrosion resistance. Yet more alloy is not a universal answer. A common kitchen grade, a hard knife steel, and a duplex chemical pipe solve different problems. Service conditions decide which trade-off is useful. Surface finish joins composition. Deep scratches, rough welds, trapped deposits, and embedded particles of ordinary steel can create weak sites. Drainage and cleaning access can matter as much as a grade number. The object on the table is therefore only half the material. The other half is the environment created around it by design, fabrication, cleaning, temperature, flow, salt, and time. Turning that conditional chemistry into millions of reliable objects begins far from the finished shine. Chromite becomes ferrochromium. Nickel, molybdenum, iron, and recovered scrap enter different grades through global supply chains. At a steel plant, an electric arc can melt scrap and other metallic feed. The difficult task is removing unwanted carbon while keeping valuable chromium in the metal. Modern decarburization vessels control oxygen with inert gas or reduce pressure. Operators adjust temperature, chemistry, and slag until the melt fits a narrow composition range. The liquid steel is cast into a solid form, then rolled while hot. Annealing controls the structure after deformation. Pickling removes high-temperature scale from the surface. Cold rolling can make the sheet thinner, flatter, and smoother. Further annealing and finishing create products ranging from industrial plate to reflective coil. None of these surfaces is merely decoration. The material then enters another workshop. A fabricator cuts, bends, draws, machines, and welds it into sinks, tanks, tubes, instruments, cladding, or valves. Every operation can preserve or damage future performance. Dirty tooling can press ordinary iron into the surface. Excessive grinding can create rough retention sites. Poor shielding can leave heavy oxide around a weld. Heat tint beside a stainless weld is more than a color. It marks a region altered by high temperature. Correct cleaning can remove affected surface layers and support a sound passive condition. But chemical passivation is not magic poured over bad workmanship. It cannot flatten a rough weld, open a sealed crevice, correct the wrong alloy, or repair a joint that traps product. For hygienic equipment, designers give fluids somewhere to go. Tanks drain, pipe joints avoid dead spaces, welds become smooth enough to inspect and clean. Seals remain accessible. The worker remains inside this material story. A welder controls heat and shielding. A finisher protects surface direction. An inspector looks for defects. A cleaner follows chemistry, time, and temperature. Chromium supplies the possibility of protection. Industrial control makes the alloy repeatable. Human judgment carries that possibility through every cut, joint, wash, and return to service. Consider a dairy after a production run. Milk residue cannot remain in a pipe simply because the pipe looks metallic. Hot water and cleaning chemicals must reach the full product path. A suitable stainless system tolerates these cycles while keeping a smooth, durable boundary. Pumps, seals, heat, detergents, flow, sensors, and trained operators still perform the cleaning. The same principle appears in breweries, commercial kitchens, pharmaceutical plants, and food factories. Stainless did not invent safe food. It gave those systems a surface that could survive their repeated methods. Now, return to the hospital tray. Its usefulness depends on more than resistance to rust. The shape must expose every area. The instrument must tolerate reprocessing. Staff must follow validated cleaning and sterilization procedures. Stainless supports this chain because it can remain durable through handling, heat, water, and cleaning agents. It does not kill every microbe merely by existing. Cleanability is not automatic sterility. Municipal water systems use stainless screens, pumps, fasteners, valves, and selected piping. Chemical plants use stainless vessels and heat exchangers where compatible grades manage specific fluids, pressures, and temperatures. Each application is a controlled wager. Engineers predict an environment, choose a grade, design geometry, specify fabrication, and plan inspection. Operators then discover how closely the real environment matches that prediction. Architecture makes the wager public. Stainless cladding, roofs, anchors, and railings can serve for decades. Coastal salt, de-icing spray, sheltered surfaces, and poor drainage can still produce staining or localized attack. The long service life often associated with stainless is therefore earned, not guaranteed. Someone must orient the finish, separate incompatible metals, wash salt deposits, and notice trouble before it becomes deep damage. These actions rarely appear in photographs of finished buildings. Neither do the cleaners who restore a handrail, the technician who opens a valve, or the crew who prepares a weld for inspection. Their work reveals what stainless changed at civilization scale. It made repeated cleanliness, containment, and visible inspection easier to build into durable equipment. It did not make those activities unnecessary. That distinction matters because modern trust often arrives through a surface. We see a bright kitchen and read hygiene. We see an instrument tray and read readiness. We see a tank and read control. Sometimes the appearance deserves that trust. Sometimes it hides a rough seam or forgotten gasket. The material can support a trustworthy system, but it cannot replace a trustworthy procedure. Its reach also depends on distant places. Chromite production is concentrated in a small group of countries. Nickel follows its own geography, technologies, prices, and political risks. A spoon may contain little nickel, while a chemical vessel may contain much more. Ferritic grades can reduce nickel demand in suitable uses. Higher alloy grades may prevent costly failure in the harsher service. Choosing a grade, therefore, connects a local object to mining, energy, trade, and price. Choosing too little can shorten service. Choosing too much can spend scarce alloy where it creates no added value. The best design is not always the shiniest or most expensive. It is the one that preserves function through real exposure, real cleaning, real human behavior, and a realistic maintenance plan. That is how an invisible film became social infrastructure. It joined countless surfaces to routines that people perform every day, often without noticing the material until one of those routines fails. The hospital tray looks clean because its upstream landscape is absent. Chromium begins in chromite ore. Nickel may begin in deep mines or broad laterite deposits, followed by energy-intensive processing. Mining moves rock and creates waste. Ferroalloy furnaces operate at high temperatures. Steelmaking, rolling, annealing, and finishing require electricity, fuels, water, acids, refractories, and transport. There is no single footprint for stainless steel. A scrap-rich ferritic sheet made with lower carbon electricity differs from a high-nickel product fed by ore-based units and a carbon-intensive grid. Service life changes the comparison again. A durable tank that avoids several replacements may justify its initial burden. An over-specified decorative part may consume alloy without providing that same return. Human exposure also changes along the chain. Solid stainless on a countertop is not the same hazard as airborne fume, created when stainless is welded or thermally cut. That fume can contain hazardous chromium and nickel compounds. Some processes can generate hexavalent chromium. Ventilation, local extraction, process choice, training, monitoring, and protective equipment become part of responsible fabrication. The distinction prevents two mistakes. Stainless should not be called harmless because the finished product is stable. It should not be called poisonous because a particular hot process creates a controlled occupational hazard. Cleaning carries its own decisions. Harsh chemicals, poor rinsing, or incompatible tools can damage surfaces and expose workers. Weak cleaning can leave contamination in equipment that still appears bright. Failure also distributes cost. A hidden pit in a pipe can interrupt production or release fluid. A rough weld can trap residue. A corroded fastener can force replacement of a larger assembly. Managers may see downtime. Workers may face repair exposure. Users may face contamination or lost service. Communities near extraction and processing may carry burdens far from the final polished object. Even cosmetic staining creates consequences. Owners may replace structurally sound material because its appearance no longer signals cleanliness. Others may dismiss warning signs because they believe stainless cannot rust. The word stainless was always an aspiration, not an absolute law. The alloy stains less under suitable conditions. Its name becomes dangerous when it encourages people to stop looking. The first improvement is often not a new alloy. It is a better decision about the alloy already in use. Match the grade to chloride, temperature, cleaning chemistry, strength, and fabrication. Remove crevices before trying to overpower them with more molybdenum. Make tanks drain, keep welds accessible, prevent carbon steel contamination. Train workers to recognize heat tint, deposits, and early localized attack. Longer service spreads the original burden across more years. Repairable assemblies and replaceable components can prevent a small failure from discarding a large object. Inspection should focus on places where local chemistry can change. At the mill, lower carbon electricity can reduce some furnace emissions. Better scrap sorting preserves chromium, nickel, and molybdenum in high-value loops. Efficient processing can reduce yield loss and energy use. Emerging routes may use hydrogen, lower carbon ferroalloys, or carbon capture. Their benefit depends on the plant, power system, ore, grade, and boundary being measured. No green label removes the need for verification. Recycling remains one of stainless steel's strongest practical advantages. Scrap can return to a furnace and become new alloy. Yet, collection, separation, contamination, and growing demand prevent a flawless closed circle. A sorter using an analyzer performs a quiet act of material conservation. Identifying one piece as a nickel-bearing grade keeps those alloying elements from being diluted into a lower-value mixed stream. Designers can support that work through clear material identification and separable assemblies. Buyers can ask about service conditions instead of selecting by appearance. Owners can maintain surfaces before local damage becomes structural loss. The future is not stainless everywhere. It is stainless where repeated cleaning, containment, strength, and long service repay the burden, with other materials chosen honestly where they perform better. The hospital worker lifts the dry tray and turns toward the next room. Nothing dramatic appears on its surface. That quietness is the result. Beneath the reflection sits an ultra-thin reacted film. Behind it stand miners, furnace crews, rollers, welders, cleaners, inspectors, and scrap sorters. Around it stand rules, tools, chemistry, and maintenance. The metal repairs one kind of damage only when those conditions allow it. People must repair the larger system through better design, safer work, careful use, and recovery. The next time a stainless surface catches the light, what will you see? An object that never changes, or a material whose survival is being negotiated in front of you?